height, weight. No more. Okay, for car, what can you measure? For car. Height, weight, width, top speed. What else? Petrol tank capacity. Okay, how big is your petrol tank? Yeah? Do you have a car? Jeremy, you have a car? How big is your petrol tank? 43 liter. Oh, okay, you know, good. Okay, 43, 50, these are common petrol tank size. Alright? Okay, so matrix is a quantitative measure of something. So you can measure software, you can measure project, you can measure human being, cars, okay, many things. Okay, software measurement. Software measurement is the act of finding out the amount or size of something. Okay, so this something again can be software, okay, it can be project. Okay, so software measurement is the act of finding out the amount or size of something. So example, project A, you want to find out the total lines of code. So what you do is, you count the lines of code in each program and then you sum them up. Okay, after you sum them up, you may get this value, okay, 10,000. So counting line of code in each program and then you sum them up is the act of finding out the size of project A in terms of lines of code. Okay, so software measurement is the act of finding out the amount or size of something. Okay, so I want you to know the meaning of matrix. Okay, so matrix is the quantitative measure of something. So example, project A, you can measure lines of code. After measuring, you get a number. You can measure pages of documentation. After you count number of pages of documentation, you also get a number. So you also can count number of defects reported by customer 1 week after installation, or perhaps 1 month after installation. So software metrics is the measurement related to software. Alright, so this is what I added. Software metrics is the measurement related to software. Okay, so after this lesson, I will put chapter 4 version 2 into the classroom. So if you did not manage to copy down completely, you can refer back to this slide in version 2 in Google Classroom. Software metrics is the measurement related to software. So software measurement, software measurement is the act of finding out the amount or size of something. Okay, so for project A, the act of finding out something is you count lines of code in each program, you sum them up, you count the total pages of documentation, count the number of defects reported by customer 1 week after installation. All this counting is the act of finding out the amount or size of something. So this something is software or is a project. Okay, so software measurement is the act of finding out the amount or size of various aspects of a software. Okay, so a short introduction is software measurement. Okay, so why you want to measure software is because we want to evaluate. Okay, reason for measuring software is because we want to evaluate the software product, or we want to evaluate the software process to see how good is the software product and how good is the software process. Okay, I'll skip this one. Okay, so examples of software metrics. So example of software metrics. So for software, what can we measure? So we can measure total lines of code. Total line of code, the short form is LOC. When you see LOC, LOC means total lines of code. Okay, so we can also measure number of errors, number of defects, so pages of documentation. So, so project A, after you measure, you may have this value, 306,000 lines of code, 288 errors, 30 defects, 205 pages of documentation. So this is for project A and this is for project B. So when you have metrics, when you have taken measurement, then you can make comparison between projects. So if you have the metrics for one project, if you only have the metrics of one project, it doesn't tell you much. So when you collect metrics for all projects, okay, when you have collected metrics for all projects, okay, then you will be able to know, okay, whether you are doing better or you are doing worse, or whether your project size is becoming bigger and bigger, or the size is the same. Okay, so when you have metrics for different projects, then you can make comparison. Okay, so example like project A 30 defects, project B 20 defects. Okay, so now you can compare the quality between project A and project B. Okay, so based on these two numbers, okay, we can say that project A has 50% more defects than project B. So how do I get 50% more? Is 30 minus 20 over 20 is okay. This is multiply. Okay, multiply 100%. Okay, so this minus this over 20 multiply 100%. So this is telling us that project A has 50% more errors than project B. Okay, so when we have different numbers for different projects, we can make comparison to see whether one is better than the other or one is worse than the other. Okay, so non-normalized metrics. Okay, non-normalized metrics show that project A has 50% more defects than project B. So the numbers here are non-normalized metrics. Okay, so they are non-normalized metrics. So let's look at the next column. So the next column here, I will show you normalized metrics. So these metrics here, they are normalized with 1,000 lines of code. KLOC means 1,000 lines of code. So the metrics given here has been normalized using 1,000 lines of codes. So meaning of normalized with 1,000 lines of code is you compare number of errors or number of defects or other things between projects based on per 1,000 lines of code. Okay, so you don't just compare using this number and this number. So when you normalize with 1,000 lines of code, okay, so you compare between project A and B. Okay, so project A, you look at 1,000 lines of code. There are how many errors and how many defects. So project B, you also look at 1,000 lines of code. Okay, there are how many errors and how many defects. So you make comparison between 1,000 lines of code. Okay, so normalized metrics will give a fairer comparison. So we got to compare fairly. So we use normalized metrics. So we can normalize with 1,000 lines of code. We can also normalize with something else. Okay. So after you normalize with 1,000 lines of code, project A, this is the number of errors. Okay, so project A has 0.9412 errors per 1,000 lines of code. Project B, 0.9102 errors per 1,000 lines of code. So you compare based on per 1,000 lines of code. So defects, this is defects for A, this is amount of defects for B. Okay, so in every 1,000 lines of code, project A has 0.098 defects, project B has 0.078 defects. So based on defects per 1,000 line of code, so project A has 25% more defects than project B. Okay, so this is how I get the 25%. So non-normalized matrix shows project A has 50% more defects than B, but when you normalize it, it is not 50% less than that. Okay, so using normalized matrix give you a better indicator, and you are making a fair comparison based on per 1,000 lines of code. Okay, so for pages of documentation, this shows that project B has more pages of documentation than project A. Okay, so meaning there are more project information. Okay, project B, you have more project information. A, you have less project information. So in terms of maintainability, okay, so which project has higher degree of maintainability? It is project B, because you have more information about project B rather than project A. Okay, so these are examples of normalized metrics. Okay, so errors per 1,000 lines of code, defects per 1,000 lines of code, so cost per lines of code, pages of document per lines of code, errors per segment, 10 lines of code per segment. Okay, so you can normalize in any way that you want, as long as it is meaningful to you. Okay, so use of software metrics. So what is the usage of software metrics? Okay, it is for quality control, for project control, for productivity assessment, and to do estimation. Okay, so usage of software metrics. So software metrics are used to control quality, to control project, example, to control project cost, to control risk, to assess productivity, and to do estimation. Okay, exercise. So match the usage of software metrics to the correct metrics. So this is, for quality control, is pretty straightforward. So for quality control, okay, you can use metrics like how many errors per 1,000 lines of code, defects per 1,000 lines of code, okay, number of errors per segment. So when you have these metrics, so let's say project A, 10 errors per 1,000 lines of code. Project B, 20,000 lines of code. Project C, 30 errors per lines of code. 30 errors per 1,000 lines of code. You see A, from A to B to C, okay, the quality is becoming worse. So to prevent from getting worse, you have to do something, since you have all these numbers. So this is how you control quality. So when you do measurement, you know, okay, quality is getting worse. Okay, do something. Okay, so lines of code per segment can help you to assess productivity. Okay, so lines of code per segment. So lines of code per segment is you determine, okay, you calculate how many lines of code is produced by a software engineer in 1 month. That will give you an idea, okay, whether the productivity is good or bad. How many lines of code can you produce in 1 month? Increasing? Decreasing? It is good, it is increasing. Okay, your productivity is getting higher. Then you finish your FYP on time. Okay, indicator. So a metric or combination of metrics will provide you insight into the software process, project, or the product quality. Okay, so 500 errors per 1,000 lines of code, okay, is an indicator that the software is of poor quality. Okay, so after measure, you found out there are 500 errors per 1,000 lines of code. So this tell you, okay, this tell you the software is of poor quality. Okay, if you count defects, so there are 0.01 defects per 1,000 lines of code. Okay, so this tells you the software is of high quality. So this is an indicator. Okay, so this is an indicator that software is of high quality. This is an indicator that software is of poor quality. Okay, so you compare this number, and this number. Oh no, you compare this and this, you compare this and this. Okay, you compare this one and this one. You can also compare this and this one. This gives you an indicator that project B has better quality than project A because project B has lower number of errors and also lower number of defects compared to project A. Okay, now you will look at these two numbers. So these two numbers tells you, okay, these two numbers tell you project B has more pages of documentation per 1,000 lines of code compared to project A. Okay, so this is telling you that you have more information about project B than project A. So in terms of degree of maintainability, so project B, I would say project B will have higher degree of maintainability than project A because when you want to modify a system, you will look back at the documentation. Okay, so category of software metrics. So 3 categories of software metrics: product metrics, process metrics, and project metrics. So product metrics can be further divided into static metrics and dynamic metrics. Static metrics are numbers that will not change. So after a project is completed, total lines of code will not change, correct? So when a project is completed, total lines of code will not change. So lines of code is a static matrix. So length of identifier and some length of variable name, okay, is a static matrix, it's fixed. So depth of nested if statement is also fixed, okay, it will not change. Cyclomatic complexity, so number of independent paths in the program also will not change. So static metrics are metrics that will not change. So dynamic metrics are value that it may change. Okay, same software. So same software when you run it, different time may give you different value. Okay, so example like time required to start a system. Time required to start a system, example time to start the WhatsApp web. You use your laptop to start up the WhatsApp web. Every time you start the WhatsApp, the amount of time taken, is it the same? Okay, not the same. That's why this is something that is not fixed. Dynamic metric is something that is not fixed. It's the same piece of software. Sometimes you look faster, sometimes you look slow. So execution time required for a particular function. Okay. So time required to generate class code. I generate class code. Okay, I click generate class code. The amount of time is shown the class code is not the same every day, every time. But still acceptable. The amount of weight is still acceptable. So this is dynamic metrics, which you may want to consider measuring if you have a software. Okay, so number of system failures. Okay, so number of system failures, example 2021 3 system failures, 2022 2 failures. Okay, so this is telling us that system is improving. Your laptop, when you press the on button, does your laptop on? Or while you are using your laptop, do you encounter system hang? Yes, sir. Yeah, 1 year, how many times? Go on, system hang. Go on. Now I seldom experience system hang with my laptop. Now I seldom experience. Where during the time when there's no internet, yes. During the time when there's no internet, system always hang. Use software, system hang. So after internet becomes so popular, we have this Outlook account. We are forced to sign up for an Outlook account before you can use Windows. After signing up account, they start collecting data. So they start collecting data. When system fail, they collect data and they do upgrade patches. So now, I would say number of failures become very rare, okay, compared to last time when they do not collect data. So system failure is also something that you can measure. So number of system failure will not be the same. Okay. So number of failure you encounter this year and next year may not be the same. Okay. So all these dynamic metrics, okay, can be measured or corrected during systems testing or after system implementation. So you can collect all these metrics, okay, all this value you can collect during testing or after people have started using your system. So this is cyclometric complexity. So cycle complexity is measuring the number of independent paths. So if the source code has only one path, then cycle complexity is 1. One path means there's no if statement. So the program is executed sequentially from top to bottom. So there's one path. So complexity is 1. If the source code contains one if condition, then cyclometric complexity is 2 because there are 2 paths. Okay. So you look at here, okay, you look at this diagram, so there are 4 paths. Okay, so there are 4 paths from 1 to 11. So from 1 to 11 there are 4 paths. Okay, so 4 more paths being more complex. So that's cyclomatic complexity, okay, measuring the number of independent paths. More path means more complex. Okay, so I mentioned to you just now product matrix. Okay, two types of product matrix, static matrix and dynamic matrix. Okay, remember software is a product. The documentation you produce is also a product. Okay, so next is process matrix. Okay, so process matrix. So process matrix, types of process matrix. Okay, so the time taken for a particular process to be completed. Okay, so this can be the total time devoted to the process, calendar time spent on the process by a particular engineer, and so on. So resources required for a particular process, number of occurrences of a particular event. So meaning for process, you can measure the time taken for the process from start to end. So number of resources required for the process, number of occurrences of particular event. So example of event. Okay, example of event, during testing, 5 runtime errors encountered. So I've changed this sentence slightly here. Okay, event, during testing, 5 runtime errors encountered. Okay, you run a software, oh, there's runtime error. Program stop execution. So this is an event. Something happened. Okay, so at the design stage, 2 requirement changes were received. Okay, so there are many stages. Okay, but during the design stage, you receive 2 requirement changes. 50 lines of code modified due to a requirement change. Okay, this is another example of event. Event is something that happened. Okay, event is something that happened. Okay, event is something that happened. You receive a change request. What happened? 50 lines of code modified. For process, okay, for process, where you can measure time. So the time needed to complete the process, resources required for a particular process, and number of occurrences. So this measure process. Okay. Process metrics give an indication of the software development process. Okay. So process metrics give an indication of the software development process. Okay. Example. Okay. Example: defects delivered to and reported by user. This will be a better example. Okay, so let me tell you one more time. Process metrics give an indication of the software development process. Okay, example: 50 defects reported by user 1 week after installation. So you receive 50 defects. 1 week after installation, you receive 50 complaints about defects from customer. This gives you an indication of the software development process. What these people are doing during the software development. So many defects reported by customer. Yes or no? This number gives you an indication of the software development process. During FYP testing, 20 runtime errors encountered. This gives an indication of your software development process. I think you are not done enough while you are developing the software. It gives you an indicator that you do all the steps, but you are not doing enough. Okay, so it gives me an indication of your software development process. Okay, so you do analysis, design, code test. You may do system test, but you do not thoroughly do unit test. Okay, so it gives me an indication how you develop the process you use to develop the software. Careless. Okay, but if during FYP final testing, no runtime errors, okay, it tells us this student, the development process is good. Must have executed all the software engineering steps. Okay, so this student, no runtime errors encountered, must have executed all the software engineering steps properly and thoroughly. Okay, so those that test encounter 20 runtime errors is careless, may have skipped certain software engineering steps. Okay, so process metrics. Okay, process metrics give an indication of the software development process. Okay, so example, 50 defects. 50 defects is an indicator that, okay, maybe there's some step is skipped in the development process. That's why there are so many defects. Okay, another example is human effort expended. Okay, human effort expended example. 2 software engineers were used in the coding stage. Okay, so 2 software engineers used in the coding stage. So this tells me that that particular development process does not require a huge number of people in the team. Okay, so project completed in 12 months. Okay, so this number can tell us, okay, so this number and this number can tell us, give us an indication of the software development process. Okay, so for process metrics, what else you can measure is time. Okay, so time per software engineering task. Okay, so the time per software engineering task. So how do you calculate the time per software engineering task? How to calculate time per software engineering task? Project start to project end. In your Gantt chart, you have how many tasks? Do you remember? Project start to project end, you have how many tasks? Let's say 50, right? 50 tasks. Project end, there's a date. Project end date minus project start date, how many days? Let's say 60 days. Okay, 60 days. So 50 times 60 days. So there will be so time in terms of day per software engineering task is 50 over 60. Okay. That's it gives you an average. This will give you an average amount of time per software engineering task. Okay. How many? Can you help me count how many? Zero point 0.83. Okay. So that's the amount of time needed to finish each task in your project task list. Oh yeah. Okay. Time on days 60, 50. Not this one. So now it's how many? 1.1.2. So it needed average. This is telling us average one software engineering task require 1.2 days. Okay. If you have this, you can use this number for future estimation. Okay. So in future you have another project. Okay. In future you have another project. You have 60 tasks. Okay. In future you have a project where there are 60 tasks. So amount of time needed will be 60 times 1.2. This is just an estimate. Okay, amount of time you need to complete 60 tasks. This is a future project. Okay, so this is a future project. Okay, so after planning and after doing some calculation, you found that there are 60 tasks. Okay, so likely this future project will require 60 times 1.2 days, equivalent to how many? So 72 days. So 72 days to complete the future project. So if you have collected the metrics, then you can use it to do estimation for future projects. This is one of the purpose of doing estimate, collecting metrics, or calculating this and that. Okay, I will skip this one. Okay, so I will skip this one. This one is going to more detail, so I don't want to go into this detail. Okay, so the third type is project matrix. Okay, so the third type is project matrix. Okay, so total length of codes. Okay, so total length, you can use total length of codes to measure project. You can use total length of code to measure project. Errors found per inspection. Okay, you can also count number of errors found per inspection to measure project. Defects reported by customer, pages of documentation. Project duration is the total months taken to complete the project. So number of software engineers required to work in the project. Number of changes to the project scope. Okay, so these are examples of project metrics. Okay, so all these are values that you can collect for a project. So for example, project A, okay, project A, you are able to determine total lines of code. So project A, you can also able to find out how many errors per inspection. Okay, so this project also you can find out how many defects reported by customer. Project A, how many pages of documentation, how many months required to complete project A. So 10 software engineers are working in project A. Project A received 12 changes to project scope. Okay, all these metrics you can collect for projects. So these are the metrics for project A, metrics for project B and C. So when you collect metrics from one project to another project, then you can make comparison. Okay, so you can make comparison. So comparison, if you look at defects reported by customer, 20, 25, 30. So this will give you an indicator that your project is getting worse. The quality of the project is getting worse. Okay, and if you see something like this, you have to do quality control. Okay, so when you see something like this, you have to do quality control, so that quality will become worse and worse. Okay, for this one, number of changes to project scope. Project A, 12 changes to the project scope. Project B, 15, 20. Number of changes to project scope increasing from one project to another project. Something is also not right. So how can we reduce or maintain? If you cannot reduce, at least maintain. Don't get try not to receive more and more changes from one project to another project. Okay, so what to do for this? If you do not collect metrics, you may not know this is happening. Okay, if you don't do this, you don't count, you don't know this is happening. If you count, you know this is happening and how bad it is. Okay, so perhaps you can do prototyping to confirm user requirements so that you receive less changes. That is one way. Okay, so project metrics. So project metrics can be collected from past projects. So you look at past projects that you have completed and you can measure. So project metrics can also be collected during the execution of current project, during the progress of technical work. Okay, example like count errors and counter per review. Okay, so pages of document per software engineering tasks and so on. Function point later on. Okay, so There are three categories of software metrics: product metrics, process metrics, and project metrics. Okay, so please take note of some of the process metrics, also metrics for project and product as well. Let's look at this example. Okay, if you want, you can take a picture. Show everything in one page can understand better. Okay, apart from that, this is the process. Okay, so this is a process. So this is a software development process. So for process metrics, what you can measure time in days or time in hours, resources required, and events. To measure process, you can count time, resources required, event. Okay, process metrics. Okay, so for process, this is a process. You can count this stage. You need how many days? You spend how many days to do this? You spend how many days to do design? You spend how many days to code? You spend how many days to test? How many days to do implementation? Okay? So you sum up, if you sum up, then it will be the time to complete the entire process. Okay. So resources required, you can also measure. So one resource is needed to do analysis. 2 are required to do design. 3 are needed to code. 1 is needed for test. 2 are needed for implementation. So resources, okay. So these are example of resources for each stage. This is the process. Okay, event. Okay, event, number of errors found per inspection. You may inspect the when you do analysis, what comes out from analysis is the requirement specification. So you inspect the requirement specification, you found there are 2 errors. You look at the design document and you found 2 errors. You do code inspection and you found 10 errors. You test the system and you found there are 20 errors. Okay? And when you implement, 3 errors found again. Okay? These are errors found at various stages. So these are errors found at various stages during development. Okay, so you sum up this. When you sum up, is the total errors found in this process. These are the errors found in individual stage. Okay, so number of requirement changes received. Received 2 during analysis stage. Received another 2 requests for changes during design phase. No requirement changes received during coding. 4 received during testing. 6 received after implementation. Okay, so total number of changes, total number of requests for changes received. Okay, so during this development process is 14. Okay, so this is a process. Okay, for process we can measure time. Okay, so the time to complete individual phase the time to complete the entire process. Resources required for each stage and resources required to complete the entire process and events. Okay. Okay, product metrics. Software is a product. Okay? So software is a product. Product metrics. Software is a product. You can measure lines of code, length of variable name, so depth of nested if statement, cyclomatic complexity, start time, okay, number of system failures. Then what's this? Requirement spec. Requirement spec is a product, number of pages. Number of pages in the requirement spec. Number of pages in the design spec. So program or source code is the product. This analysis will produce requirement spec. Okay? Analysis will produce requirement spec. The requirement spec is the product. Okay? So this one you can measure number of pages. So design, you will produce design spec. You can measure number of pages. The coding stage will produce program or source code. So source code, you can look at how many lines of code, length of variable names, depth of nested if statement. So the executable file, okay, so the executable file or system start time, number of system failure. So when you do testing, the product or the output are test plan, test cases. Okay, how many test plan, how many test cases? So implementation, so change over plan, how many pages? Training material, how many pages? The purple color represents product. Any other product you want to add? So for this, what you can measure? Number of pages. You can measure also number of pages. Okay. Process metrics. If you do for you your FIP resources is one. Also one, because you are doing it solo. You are doing solo, so it's one. This can be 1 or 2 if you're asking friend to help you to test. Can be more than 1. You don't do this. This one also you can count. You can ask your friend to check. See how many errors in your requirement spec. How many errors in your design chapter? Okay, ask your friend to help you look at your code and check, see there are how many errors. Okay, if you don't want friends to help you, you can test your own program and record down how many errors. Okay, so process metrics. And product metrics. Okay, now project metrics. So what you can use to measure project: lines of code, number of errors found per inspection, defects reported by customer, pages of documentation, duration, resources required, requirement changes received. So these are the numbers you get for project A, project B. Okay, so project A, project B, A20, B10. Okay, so quality is improving. It's a good sign. This is also a good sign. You receive less requests for changes. Okay, so there's one thing that I want to highlight to you here is this, and this. So, number of errors found per inspection, number of requirement changes received, this and this can be used to measure the process. So the same can also be used to measure the project. All these metrics is they are not exclusive. Okay, so they are not inclusive. So the one metrics can be used to measure project, the same metrics can also be used to measure process. That's the meaning of here. Some of the process metrics are also metrics for project and product as well. Let me continue a bit more. Okay. So size-oriented metrics, okay, software measurement. So there are two. One is size-oriented metrics and function-oriented metrics. Those that I've discussed with you just now, they are size-oriented metrics. Lines of course, effort, month, okay, cost, page documentation, number of error, defects, okay, people, software engineer, all these are size-oriented metrics. Okay, so these are size-oriented metrics, okay, not normalized, and these are size-oriented metrics normalized. So this is normalized by using software engineer, normalized by month, normalized by lines of code. Okay, so alpha and beta project. Okay, alpha and beta project. Alpha project, 12,100 lines of code. Beta project, 27,200 lines of code. Okay, so we can normalize in such a way that we want to see what's the lines of code per software engineer. So lines of code per software engineer is 40335440. So what does it tell us? This tells us the productivity of the software engineer. Okay, so this tells us the productivity of software engineer. So this will tell us, when you do this, it will tell us cost per line of code. Productivity. This will tell us the productivity. Okay, how many lines of code produced per month. This will tell us the cost per line of code. Okay, so this will tell us the cost per line of code. And this will give us an indicator of quality. Okay, so you look at this one. Okay, just looking at this one first. Alpha, in alpha project there are 134 errors, beta 321 errors. So looking at this rough number, so here is telling us that project beta is worse than project alpha. Okay, but when you normalize it, okay, you find that it is indeed beta is worse than alpha, but it is a small difference. Okay, it is a not small difference. It is not a big difference in terms of quality, as you can see here. So normalized method will give you a better picture. Okay, and here alpha project produced 12,100 lines of code. Project beta produced 27,200 lines of code. Okay, so if you do like this, okay, lines of code per month. So it tells you a different story. It looks like beta. It looks like beta project and productivity is higher than alpha because it produces more lines of code. Okay, but actually it is not. Okay, it is not. It is alpha that has a higher level of productivity. 504 lines of code per month compared to 438 lines of code per month. Okay, so examples of normalized size-oriented metrics. Okay, so all these are size-oriented metrics, errors per 1,000 lines of code, defects, cost per lines of code, etc. Okay, so KLOC is 1,000 lines of code. KLOC, okay, is a short form for 1,000 lines of code. Let's take 5 minutes break.